Okay, so we talked about um, the design process, and we're getting moving towards this idea of Kanban boards. And you notice that with the design process, a lot of times you're using things like sticky notes, you're putting them on boards, you're building these larger structures like swim lanes, you're doing all sorts of organization work. And so the design process is like kind of the first step in the project. Then you move on to the implementation steps, testing steps, and so forth. You move from development to production. And to do all of that, you need a Kanban board, which is sort of like a design process, except you're creating, instead of putting ideas together and stringing them, say, into workflows, you take issues and you put them into categories of priority. And so we'll go over Kanban boards next time and how they can be good for your project and how they cannot fit your project very well. But the big idea here, and there's an article on this, is to make ideas consistent with your project workflow. So if you're designing for a small project, you don't want to use workflows suited for a big project, vice versa. Same thing with roadmaps, where you want to have like a roadmap that you have like a 10-year window to do something where you only need a 2-year window, or you say you're going to do something in a 2-year window that might take you 10 years. And so there's this sort of complexity that creeps into your project throughout the design process onto the Kanban board. And that is that you can have this proliferation of ideas and this proliferation of issues. We usually think about those as being kind of like, great because we have more ideas, the better, and we can just sort them out later. But in fact, we've talked about scope creep and how that can increase the scope of your project, which is bad. It can be over scoped, and we'll talk about rescoping and descoping next time. But also that, if you are in certain areas of, if you inhabit certain areas of the world, say you're doing something like drug design, or you're doing something like trying to build a social system, as opposed to building a small mobile app or a website where sort of the processes that exist, and it's pretty self-contained. You can have this sort of problem of complexity, and it creeps into these different phases of the design of the project um, cycle, and you have to learn how to deal with those complexities. So that brings us to a question, which is, and again, I said that when you take project management, your assumption is that I'm going to teach you methods on how to sort of get control of a project, how to make it simpler, how to master organizing teams, organizing resources. And we've done that. But also you have to consider that a lot of this complexity is inherent in technological projects. So can we tame the complexity that's inherent in technological projects? And so the answer at first glance should be yes, we should be able to find ways to tame that complexity. And then I ask, if so, why? So maybe we don't want to tame that complexity. Maybe we want to harness that complexity for all it's worth. Or maybe we want to manage around it so that we, don't kind of oversimplify the problem and end up failing in our project because we didn't consider all of the sources of complexity. So we can have these linear problems like the staircase, or we're going to have this very convoluted problem like this example of something I'm going to talk about soon, which is a wicked problem. And there are different aspects of managing both of these types of systems. Okay, so I actually promised that I'd talk about this book. This is where, this guy, Kevin Kelly, who is a technologist, this is a book from back in the 1990s. So if you go read this book, it's available on PDF format online. If you go through this book, it's kind of a nice read. It talks about these technologies of adaptation that we talked about in the last lecture, but it also talks about how we have some systems that we work with that are not controllable in the same way, say, like building a website is. And open source projects are kind of like that, where you have all these tools that you have to manage, and you have contributors coming in and leaving and there's a lot of flux, and you end up with a lot more complexity than you bargained for sometimes. And so in open source project management, this is an example of one of these technologies of adaptation and some of the things that Kevin Kelly talks about in Out of Control. And there's a strategy called keeping things under control. That doesn't mean that you control every process. It just means that you have enough oversight to keep things under control, to keep things from tipping over into chaos or into some other, realm of disorganization. So that's a distinction I think to make in a lot of projects. Sometimes you can have these very tightly defined workflows, tightly defined roadmaps, but sometimes you just can manage to keep things under control. Not necessarily control every aspect of them, but just to keep them from tipping over to something more chaotic. So it's worth revisiting the idea of information technology and how that is inherently sort of a complex system. So if you're dealing with something like an IT network or something in IT, oftentimes you'll have information technologies, which at first glance appear to be something that you can control pretty well. But because you have humans in the loop and you have other types of things going on, these information technologies are intertwined with complexity and difficult nonlinear problems. So this is especially true when you start scaling up your project. Say if you have a small team, it's easy to control what the small team does in assigning tasks. If you scale the team up, especially if it's an open source project, where you have people participating a little bit at a time, and you have hundreds of contributors, and you have to have people who can sort out who's issuing a pull request and what that pull request is for. And then, okay, this person is joining this team, but then they've left and another person is taking over. That becomes pretty hard. There's a lot of complexity there. It becomes pretty hard to control that. And it's easier to just keep things under control than to sort of try to build a workflow that's tightly controlling that process. Furthermore, when you deal with social systems, when you interface with social systems or what they call socio-technical systems, you have these difficult nonlinear problems that emerge. So if you go from like a local network to the internet, that scaling up and that inclusion of different, heterogeneous groups of people, people with different technical skills, people with different needs, that's going to increase the likelihood of difficult problems and things that you can't necessarily manage your way out of. So these are examples of all sorts of different socio-technical systems, the internet. There are all sorts of different, multi-team, uh, uh, multi skilled things that you can have in your projects that um, can be hard to manage. So we talked about these socio-technical systems. Socio-technical systems could be, open source projects. They could be the internet. They could be other types of IT problems, or they could be other types of things we haven't talked about in the class. They can also involve different types of domains. We had that chart where they talked about how easy it is for teams to improvise. And so I think when you have a high degree of improvisation, that also tracks with this idea of having difficult nonlinear problems that you have to be able to solve in that improvisational way. So if we think about socio-technical problems, and that is where you have social systems that interact with complex technical systems, they often create problems that are hard or intractable to solve. And so this is not something that's even new to IT. This is something that's gone back to things like urban planning or back to like telephone networks. And the idea is that we have these socio-technical problems that are intractable because they have a number of properties that make them hard to solve or hard to control tightly. And so these are what they call wicked problems. And wicked problems have a number of properties. They usually have some input, but the input is goes through such a complex sort of set of interactions that there are both multiple solutions and there's no good solution to a problem. So wicked problems have a number of properties. The first is that they lack clarity in their aims and solutions. There are challenges of articulation and their internal logic. So again, when I tell you about like projects and say, we're going to do project management, and your assumption is that we're going to be able to solve all problems that come before you. You manage your teams optimally. And indeed, a lot of the methods that people advertise, from agile to waterfall to lean to whatever, they assume this sort of like ability to clearly delineate the problem, have a logical solution, and then be able to kind of find a solution that maybe a one size fits all solution, but definitely a solution that fits a specific team. And indeed, we've seen that that's not always the case. In the case of wicked problems, and a lot of times you'll be dealing with these problems and you won't foresee it. You'll think that you're in a domain that is very clearly, where problems should be easy to solve. But sometimes you'll have these times in your project management career where you can't really figure out what the aims and solutions are to a problem. So it's really hard to sort of apply the project management methodologies to these kind of problems. Wicked problems are also subject to real world constraints that prevent quick solutions and replication. So sometimes you have problems that require a long-term solution. Sometimes you can't give short-term solutions to those. And sometimes the solution that you give you have maybe a problem that recurs. Sometimes you have a solution to the problem one time and it doesn't work the second time for reasons that you can't figure out. So that's always a challenge and it's very frustrating, but that's the world we live in. It's very complex. Also, wicked problems are impossible to solve in a way that is simple, complete, or final. So you can't necessarily, again, if you solve a problem with a socio-technical system, sometimes that problem will crop back up. Sometimes it'll lead to 6 other problems, and you have to solve those problems, and those problems lead to other problems. So, it can feel like playing a game of whack-a-mole, but it's just the nature of that system. So it's something that you need to design into your project management strategy. But socio-technical problems are also path-dependent problems. And so these, sometimes depending on your input, depending on your initial condition, it gives you certain outcomes. So, for example, there's this old idea of if a butterfly flaps its wings, it's an input to a complex system, namely the atmospheric system that leads to certain weather that occurs. Either, you might have a hurricane or you might have a thunderstorm because of some instability that was introduced into the system. So to put that in a less abstract way, you might have someone issue a pull request and it might create a cascade of events that leads to some big scale problem in your software. And indeed, that happens a lot in software where you have small bugs that perpetuate themselves, where they cascade into larger problems. And they don't get caught by the team because they don't have an ability to, they don't have an ability to kind of manage every aspect of what's going on in the software, every bug. And so you end up with this problem. And so this is, again, there are problems that are path dependent. So you can actually develop strategies to look at path dependence. You can also develop strategies that allow you to sort of just manage things at a high level. You can have strategies, for example, for bug reporting. You can have strategies for managing technical debt that might catch these problems before they perpetuate or they propagate to larger scale problems. So just to give you an idea, if you were to look at something that's kind of in the real world or in the virtual world, as it were, you can have an example of taking our campus and thinking about what happens if we want to build a digital twin of our campus or digitize our campus. So this is an example. This is a screenshot of North Campus. And so, we have buildings, we have open spaces, we have infrastructure, we have people interacting with each other, we have traffic, so we have vehicles, we have events, all sorts of things that are going on. And so if we want to, build a digital twin of the campus, we could just build like a copy of this map, and that might be sufficient. Say if we wanted to build an application to monitor North Campus in some way, like, we wanted to plan traffic flows or something. Um, if you think about like a simulation program like SimCity, that's what they're trying to do. They're trying to replicate the real world of a city, but they're trying to simulate it. So the question is, how realistic do you have to be? And so, but let's think about this in terms of we want to sort of model the campus for purposes of, say, just having an app that determines when people are going to class. So you'll need to actually model a lot of things for that. You'll need to have, say, for example, a model of libraries and a model of building scheduling and access, a model of transportation, campus events, weather, the campus physical state, social interactions, and other things. And so, you can add as many things as you want. And you quickly begin to see that this becomes very complex very quickly, that it's hard to manage all of these things together, and that your original task, which you thought was simple, is actually very hard, and you've not really scaled the project up to include um, more area. It's just that problem because you have to think about all the things that are involved in and interact with that, it becomes a harder problem. So this is an example of, where I'm trying to build a project and I'm getting all this complexity, and then I have to manage it, and it's very hard to manage it. So, you might ask, if you're like, say, an engineer, and engineers ask this all the time, but also if you're just kind of wanting to not deal with complexity very much, you might ask the question, is linearizing the problem the answer? In other words, I can go back to this campus and say, look, this is good enough if I model transportation and building scheduling and access and be done with it. And it linearizes my problem because it just reduces the number of interacting components, and I can measure these things and provide something, and it's less code and everything else. So, people will tend to simplify things in their projects. Sometimes we won't, create workflows for every instance. Sometimes we won't create very many issues. We try these approaches like lean, which are like where you just strip everything down to like a very, limited type of, model, like we've talked about with agile, where you don't have documentation, where everything is assumed to be communication and it works perfectly. And that's just the assumption and it should work. So you might just say, do that. And so isn't that just the best way to do it? So, you could say, well, why do I care about, say, like everything you're talking about? Why do I care about documentation or anything else? Why don't I just manage my team just as like, just go to get a book on agile and go read it and put it into practice? Well, the problem is that may be good for some projects, but not always. And especially you have to consider that underlying system that you have. Is the domain you're working in something that's like lends itself to that sort of lean management, that sort of like minimalist management? And so the answer sometimes is yes, but oftentimes it's not. Oftentimes you have to deal with the complexity. You have to deal with things, especially if there's socio-technical systems that provide these wicked problems. You have to hit that head on, and you have to have methods to make that happen, to make, to sort of manage that complexity. So I've been kind of alluding to this figure for a while in the lectures. And this is a project management approach called Sinafin. And so Sinafin is different from, say, like Agile or Waterfall, in that the idea isn't to manage the project per se in terms of its phases or in terms of the practices. It's really about sort of managing the domains of knowledge. So this is Dave Snowden who developed Sinafin. This is the original citation. So this is about 20 years old, this methodology. And what they do is they basically break down problem domains into 4 areas. So the first is clear. And this is kind of the assumption of agile and waterfall and all your methodologies that are kind of like lean, that you have a known and familiar process. And so it's easy to like make your issues, it's easy to build your workflows, it's easy to manage, your roadmap, so you know where you'll be in 5 years. It's pretty easy to know. It's pretty easy to assign people to tasks and all of that. So say in this case, this gremlin up at the top and this robot are both working in a milk assembly line. So they're putting milk in bottles and they're sending it out to the world. And that process, it's an assembly line, so it's pretty straightforward. It's pretty linear. We know how to do that. We know the process. We just put it into practice. Okay. So sometimes that's great, and you can apply all sorts of project management methodologies to it. Sometimes, however, we fail at even the clear case and see this gremlin falling down this cliff, and that's because they somehow botched the clear process that they were supposed to follow. So they have to recover from that. And that's when you can have a complexity kind of creep into your project. And that's maybe when it's bad because it's due to some error, but you still have to deal with it. You still have to clean up that mess. So you still have to get back on track. So, the clear case is good to understanding, like, we know how to deal with that. We don't necessarily know so much of how to recover from errors or recover from problems in the process, but that's sort of the domain of these other areas of knowledge. So the next, if you look at this ladder down here, it goes down to complicated, which is not clear, but it's also knowable. So, clear is where you have a known and familiar process like an assembly line. Complicated is where it's knowable. So we can build, say, a process, but it's unfamiliar. So you may not know how to build something. Like you can imagine the first cell phones. People didn't know how to build those right off the bat. They knew different industrial processes they could put together. Once they figured out how to build the cell phone, they could build an assembly line and build them and put them into production. But so it's a knowable process, but it's unfamiliar. You have to do some research. You have to think about how these things fit together. And in that process, there's a lot of complexity. So sometimes you're trying to solve maybe sometimes wicked problems, but once you at least get a handle on that problem, that you can build up to the clear case. So again, complicated, you can go from complicated to clear, but you can also fall down the vortex of confusion downward to the harder cases. And again, that's due to error or some problem that you've had in kind of managing that initial complexity. So we have clear and complicated. Then we go down a step, another ladder further down, and that's complex. And I don't want you to think of this as like being the fault of teams. This is really just the way the world is. So depending on the problem domain that you've selected, you may have a complex problem, a complicated problem, or a clear problem. Sometimes people try to make a complex or complicated problem into a clear problem. Like they'll just assume that all we need to do is just run our project like an assembly line, no matter what the underlying problem is. And that should be all the project management we need. That's kind of this linearizing idea. So, but the problem is it doesn't work that way. Sometimes things, it's known, sometimes it's knowable, so you have to gain knowledge. Sometimes it's unfamiliar, so you have to gain some sort of map to guide yourself. And you can't just automatically, build, say, an assembly line for something you don't know how to build. That's basically the idea. So in complex, we have things like they're doing experiments with a beaker and with a Bunsen burner, and that's just basically the idea that you're doing a lot of experimentation. And I would fit something like drug discovery into complex. I would fit something like building new technologies into complex. So when you're building the first cell phones that were built, they had to go through this complex phase where they had to kind of experiment with different designs and figure out how to do this, and then get to the complicated phase which was how to build these devices. And then you get to the clear phase, which is actually scaling them up to production. So you can produce like 1 million units of them with a low error rate or a low rate of defects. So the complex is the unknown. So oftentimes, say in drug discovery, we have some information about a drug target. We have some information about different, the efficacy of the drug, but we don't know enough to, kind of test it and see where it works and where it doesn't. So there's a whole huge unknown region here that we need to explore and find answers. So that's complex. And then there's chaotic, which is unknowable. So when we talked about quantum computing exists kind of between the chaotic and the complex. The chaotic being that there are going to be some things that people set out to do in quantum computing that are going to not be possible, or at least in the near future. So you have that roadmap where they have all these things they want to do. Some of those things they will not be able to do because they're just unknowable, or at least right now they're unknowable. So this in the graphic here is where we either reach this chaotic region through failure or just through kind of not having any clear. Sometimes you don't have a clear idea of what you want. And sometimes you're just in a problem domain that you don't have enough information to move forward on. So the shorthand here, these gremlins lighting each other on fire, one's on fire and the other is trying to put them out. So the implication here is that this is due to maybe some errors in the project management procedure. Sometimes, though, that is due to just the problem domain you've tried to tackle. A lot of these very hard socio-technical systems fall into this chaotic category. And it's not the fault of the team. The team might be wonderful. It's just that they cannot tackle the problem, or you're trying to fit this clear model of project management onto a chaotic problem. And so that's why you're falling down the cliff here, because you haven't made the right fit. All this is to say that we have this typology of project domains, and that if you're going to select a project management style, you should figure out pretty quickly what your project involves. Does it involve known processes? Are they familiar to your team? Can you know at some point, maybe within 6 months, how to do things? Or is it something that you can't know because you don't have enough background research, or can't know because we just don't even have good models for doing the research? And so this is all, I think this is a good model for thinking about complexity of projects, because that's something that a lot of people don't think about when they think about implementing a project management strategy. So again, the complex and chaotic domains, I think, are particularly important here because we think of like failure as like being disorganized, but sometimes it's just not really the fault of a team. It's the fault of the problem domain. So we don't always want to linearize things. Sometimes we can, but oftentimes we can't. So we need to find alternatives to the linear. And that's where we want to characterize the unknown and unknowable, these domains here, complex and chaotic, as a strongly interacting and nonlinear system. So if we understand it in that way, we can get a better handle on it. Or maybe we need to, we need to unlock the secrets of quantum computing before we can move forward with doing quantum computing experiments, stuff like that. So sometimes we have to think of things in terms of a dynamical system. In dynamical systems, we have, instead of thinking things as, the step-by-step process, we have these trajectories that tend to find these chaotic attractor basins. And sometimes those basins are stable, sometimes they're unstable, and thinking about the project in that way. So it's not a linear process, a step-by-step process. It's looping through a bunch of things to do and then kind of figuring out what the most stable solution is to a problem. So even then when we talk about uncertainty, and this is something that you need to kind of figure out as you're working through your project, so you need to step back sometimes from those issues and think not just about those compartmentalized issues, but about the sort of the system level, like what is uncertain that you need to kind of nail down. And then when you address those uncertainties, you can find that they have informative components. So sometimes you have to think of your project as a dynamical system, which kind of evolves over time. You can think of that roadmap as having this trajectory across it. I'm moving from the beginning where I have many uncertainties and I'm moving towards some milestone where I have fewer uncertainties and another milestone where I have even fewer uncertainties. And then eventually maybe I can get to a deliverable. So sometimes we have these mass interactions. Sometimes we have these trajectories that help us to kind of refine the project. And, thinking in terms of historical contingencies is important. So when you think about a project, when we start off in a certain place, a lot of things happen in the project. And then that history leads to contingencies. So the route through our project is basically littered with prior decisions. Whatever decisions we make lead to us to a new point. And then, so we can think about what was or the history. We can then think about contingencies that lead to the current trajectory. So, what about like what we did in the project or what are we going to do is going to lead us to some trajectory that's stable or is in a known place. So we can consider the history, we can consider the present, then we can consider the future, which are that current trajectories lead us to future possibilities. So when we think about the decision making in our projects, we say, okay, what are the things that we're doing that we've done in the past? How did those things lead us to the present? The present leads to these current trajectories. It may not be just one trajectory. We might have many possible trajectories we can follow, and then which ones are the best. So this is very different from like agile, where you're constantly reporting and doing iterative design. This is more along the lines of like just thinking about all the possibilities, thinking about different interactions between team members and resources, and then thinking what the best path forward is, not necessarily the optimal path, but the best path. So we can learn a lot about like, how to manage our project just from wringing the uncertainty out of it and finding the informative components. We're not linearizing our project. We're not creating like this step-by-step roadmap, or we're not creating this step-by-step process where we're tightly managing everything. We're just thinking about all the ways in which our interactions can lead us to success. So trajectories are the key to understanding and extracting potential orderings from a chaotic dynamical technological system. So there are a couple of examples of this. The first example are long-term open source projects with a lot of forks and contributors. If you remember that Linux fork tree that I showed you earlier in the class, you notice that it started with one project, with a core project, and then you have all these branches that emerge and forks. So you have forks that are specialized for different things, forks that are sort of alternative versions of the project. And the reason people fork those is because they see different opportunities to move forward in their own domain. They're not linearizing the process, they're making it more complex and they're solving their own local problems and they're finding stable states within that space. So that's one example of this where you have sort of a mode of production, this open source mode of production. It produces these forks for specialized purposes, for sort of maybe alternative purposes, maybe keeping the project alive, maybe creating, um, different types, different sort of versions of something, and then, kind of finding the stable states and the project evolves in that way. And it's a different way of management than like a tightly defined top-down management style. It's very, very different than that. The other example is that technological innovation can happen in a given area of technology. So sometimes, we create technologies and we do that with not necessarily the eye to the future, but if we move into the future, we can look back and clearly see that there's this progression from like, Apple II to the current Mac that we have today. And in fact, it's not a straight line progression. It's just that decisions were made at certain points to build upon something, and that led us to this point today where we have a much clearer idea of what, you know, a Mac should look like. But we didn't know that from the start. We had to sort of work our way up. And the only way we can understand it is by looking retrospectively and seeing. And so the problem there is that, sometimes we're reliant upon contingencies. So if we make the right decisions, we're in luck. If we make the wrong decisions, we're not in luck. And that's the best we can do. So we just have to kind of make the best decisions when we can. And, wherever they lead, it's not necessarily our fault. It's just the way that the world works. So here's our Red Hat family tree that I just talked about. Remember, we have all these forks. Some of them die off, some of them persist. We have forks of forks of forks. Some of those die off, some of those persist. So we're managing the complexity here. We're managing all the use cases, all of the potential of this technology. And wherever it leads, but we're not tightly controlling the design of one specific platform, managing every feature and all that. And so if we go back to the Apple Mac example, a lot of times what will happen in terms of technological innovation is where you'll be at a certain position in time, and then you'll have local decisions that you can make in terms of how to manage or how to move forward with your project. And it goes back to the sign-in method where we looked at like the known. And if we know the future, if we know where everything is going in the future, it's very easy to make these decisions. But if we don't, if we're in the unknown or the unknowable, we can only make local decisions. That is, let's just plan for the next feature and see where that leads us. And so we might plan for the next feature. We might have to plan against like shifts in technology. So if new chips become available, or there's a sea change in the way we build computers, we follow that. And so then we end up with this sort of model of something called the adjacent possible, which is where we make these local decisions and it moves us to a new square. And then every time we move to a new square, it opens up new possibilities. And we keep doing this over time, iteratively, until we reach a point in the future where we get a viable project, a viable technology. And we can look back and we can say, oh, that was great. That was the way to manage a project. But you can't manage it retrospectively. You can only manage it from the options that you have available to you. So in practice, what you're doing is you're starting at a starting point, an initial condition, and you make a decision. And you have many decisions in front of you. You just make one decision. And then from that decision, you can make other decisions. And you keep moving until you get to the best point that you can find. So again, you're in that unknowable space in the sign-in framework. And or the unknown space, and you're just trying to explore ways to move forward. And you end up moving through a complex space of options until you find something that's pretty good. And so that means that sometimes projects will fail just as much as they'll succeed. But sometimes that's the hand you're dealt. Sometimes that's the environment that you have to work in. So the other point about this is that when you use this sort of adjacent possible method, you end up with these trajectories that are constrained. So you can't explore every option out there. You can only explore the options that are immediately available to you. So if you want to get up to this upper right-hand corner square, which might have like success written all over it, you can't necessarily get there because there's no clear way to get there. You may need resources that don't exist or technologies that don't exist. So you might just be constrained to these options, these local decisions, local options, and they might lead you away from success. But again, there's nothing you can do about it. There's no way to manage your way out of that. So again, linearization is not the goal in and of itself. It's not the goal to go from the unknown to the unknowable to the, not clear to the clear. So, moving up that sign-in hierarchy. That sort of linearization is not the goal in and of itself. It seems from that diagram that it is. And some people like to follow that. They say, well, you can learn something, you can learn new things, and then get to a point where you don't know the process very well, work out the process, and then eventually you'll have an assembly line that you can build things and scale things up and have no consequences to that at all. But that's not always the goal. In fact, it shouldn't really be the goal unless you know that that's something you can achieve. A lot of times when people try to do that, it leads to misunderstandings and poor systems integration. In other words, it leads to team dysfunction, it leads to project dysfunction. You poorly estimate the time to completion because you have in your mind that you need to get these things, you need to understand these things better. And eventually, when you do, you can just automate everything or create an assembly line and make things a lot easier to scale up. And a lot of projects simply aren't like that. Sometimes we have other things that are, kind of properties of our project. Sometimes we're dealing with socio-technical systems that have so many interactions that we can't understand them very well. And no matter how hard we try, they may have some order to them, they may have some way to explore them, but you can't necessarily get a very optimal solution out of them. So we call these hairballs, which are these networks of interactions that they may have some order, but they don't really have a good optimal solution hidden in them. You just can maybe estimate the solution to some problems and, just basically manage the complexity, and that's the best you can do. We also have sometimes we intentionally embrace suboptimal design to account for technological effects. So a lot of systems will have certain second order effects. Sometimes you'll have, social effects of people interacting. Sometimes you'll have psychological effects. Sometimes you'll have to account for future interactions. A lot of times this is true with IT systems or with the internet or with social media, where you have these, you have these interactions between, say, users, but they create their own social bonds or social interactions. And then they have, every user, every member of your community has a psychological state, and you have to manage that. And then you have future interactions where you might bring in new people, and those are all different. So you can't be optimal in designing your system. You have to be intentionally suboptimal. And in doing so, you have to be flexible in terms of how you manage everything, from the issues that you create to sort of the workflows and roadmaps that you create. Okay, so sometimes the complex and complicated are addressable. Sometimes it results from hidden complexity. So when I give you this typology and I say, you know, I give you the false choice of saying, okay, maybe you can let's try to move from the complex or from the chaotic to the complex to the complicated to the clear. And you're like, okay, and you figure out a way to do that. And you think, well, okay, this is just a matter of practice. So you might say that chaotic is novel practice. So you might just try new ways to manage the chaotic. And then complex is an emergent practice. So, a novel practice would be creating issues, throwing them up in the air and seeing if people can solve them. And that takes time, of course. But let's say that you're able to put together a workflow from that. So that's emergent practice, where you can take a bunch of issues, have people on your team try to solve them, figure out the ones that you're able to solve, and then string them together into a sequence that forms some sort of workflow. And then, of course, then you want to refine that, so that moves you to complicated, and then clear, which is best practice, which moves you to something you can do quickly. Now, sometimes it'll work and sometimes it won't. Sometimes you can address this movement from chaotic to clear and also prevent moving from clear backwards, maybe to complex or chaotic. But sometimes it's just obscuring complexity. In other words, things are chaotic because the system you're working with is chaotic. And sometimes you just need to try these issues because you have no other option. Because you certainly don't know how to deal with the system you're working with. So, again, if you're working in quantum computing, you need to develop tools. You need to know how to start developing tools. You need to know more about the fundamental science. And that's sort of this novel practice. And so you're stuck there working in the novel practice area. And it's not because you're failing to make progress. It's just that there's so much in that, complexity that entails getting from novel practice to emergent practice that you spend a lot of time on that. And it looks like failure, but it isn't. It's just that hidden complexity that you didn't really consider. And so, also you have to think about complexity as when you build a system from the ground up, especially if you're building something like software, that complexity accumulates as programming abstraction increases. Now, a lot of you, I don't know how much programming you've taken, but I'll kind of walk you through this. So, we might start with working out a problem for a program. And let's say that it's a really kind of fundamental problem. So we're building a program for machine code, and then we're trying to build like higher level code like Python, and then we're going to build a UI. And so your team and your community are going to interact with the stack at certain points. So first thing we have on the left is machine code. And machine code is really not, it's really kind of taking something that you want to do and reducing it down to zeros and ones. And that requires a lot of like, you know, um, abstraction and working on that. But it's machine code, so you can get it running. If you know what you're doing, you can do that. But then you have the machine code, and then you want to build Python on top of that. So you want to build a higher level abstraction where you have you're taking the machine code and you're writing, formal data structures, and you're, working that way. And so you have another team that interacts with the Python code, and there's machine code underneath it. And the machine code needs to be good and optimized, but the interaction between the machine code and the Python are going to increase complexity. And so there's an accumulated complexity. But then you want to build a UI on top of that. And so a lot of times people think, well, just building a UI is pretty easy. But it isn't necessarily, because you have all this hidden complexity underneath. You have this Python and machine code that's sort of underneath that UI. So when your third team builds the UI, they're not only trying to solve that problem, and there are, of course, social interaction problems they're dealing with in addition to the design problems, but there's this hidden complexity underneath that can trip them up. So you have three teams working on three different phases of this software, and the complexity accumulates with each step. As you pass it off to each team, you add complexity. And so sometimes this, I don't know how to solve this problem. This is a problem in programming that often happens. And usually the way it gets solved is to reverse engineer things or to kind of solve the problems as they come along. It's not something that we can easily solve. So it's just food for thought, and thinking about how, when you scale up your project to different phases, how you can introduce more and more complexity instead of less and less, which you would think if you get to the point of a UI that makes it so simple, but it doesn't necessarily. So this is a video from the Handmade Cities YouTube channel. Why can't we make simple software? Again, why can't we make simple software? And there are a lot of good things in this video. One of the things is model reality gaps. So this is where, programmers approach a problem by taking a problem in the real world and creating a computational model of it. And then that model, it could be like a model for the web. It could be like a model for, like Python, where you take the problem and reduce it to some data structure or some set of functions. And, a lot of people get excited and they try to build this, cool piece of software that's trying to model everything in the world. And of course, you can't do that because the program would be way too long. So you tighten it up, you reduce the complexity, and in doing so, the model doesn't actually map onto the problem domain anymore. Sometimes the model never does map onto the problem domain. You create something too simple, and so it doesn't really solve your problem either. Sometimes when you take things out of the real world and you try to model them in programming language, that model can be lossy, which means it loses information. And in losing information, it's hard to kind of recover that information to get around that complexity. So yeah, there are a lot of examples from W3C and other things. So if you're interested, you can watch that video, and it's kind of an interesting take on sort of complexity in the software domain. Another example from this video is where he talks about complexity homeostasis, and this is where you have code complexity over time. So he thinks about it in terms of this homeostatic approach, where you have sort of a set point for your project, and you have a set point for how much complexity your project can tolerate, or you can tolerate as a person, or your team can tolerate. And so, it's all about, sometimes you have challenges to that level of complexity. In other words, your team might understand a process, and you might have a certain amount of tolerance for dealing with a lot of different things at once. But if you have a small team, or you have a team that doesn't have certain talents on the team, you might have a lower set point for your complexity threshold than other teams. And so you have to consider code complexity in light of your team, what they're capable of doing, how much time you have, et cetera, et cetera. And then thinking about your problems multiplying, and he introduces this concept of the hyperspace, which is where, as your problems multiply, sometimes this involves like thinking about your software over multiple versions. So he has this example of, if you have something like, if you have a problem where you want to design software, but you want to support multiple browsers, that's kind of like 3 versions of your project. And then if you have previous versions of your own software, each of those versions increases your complexity because you're thinking back to how many versions of your software you support. So you have to make things backwards compatible to some point. Then you might want to support different screen sizes as a feature. So you have 3 screen sizes to work with. Then you have maybe 3 platforms, like you want to support Mac OS, Linux, Windows, or mobile. So you have different platforms. So that if you add those or you multiply those together, you get 108 combinations. So if you want to add in multiple features, and this is something I think I alluded to before, where if you keep adding features into your software, we talked about this in the technical debt lecture. If you want to keep adding features to your software, you think, well, I can get around complexity just by adding in features, and we can kind of manage complexity that way. Well, according to this approach, you're actually adding even more complexity, and you're building this sort of hyperspace model where you might want to do one thing, but you end up with 108 combinations of that thing. And 108 combinations is hard to manage because every combination has a bug in it, or it could have new problems or something else, and you don't know. So, in this case, adding one feature in a lot of different ways, in the ways you want to do this, can, lead you to a huge amount of complexity. So that's an interesting point about like you know, how you should manage complexity, how you should think about it. So, I'm kind of arguing, instead of arguing for this sort of top-down management style, or even this sort of distributed collaborative management style, to sort of take this reciprocal and sometimes circular and futile path to success. And sometimes you need to do that. Other times you get caught in this sort of circular, futile pathway, and it's no fault of your own. You're just stuck in the complexity. So, how do you get yourself out of that? And so, going forward, if you think about this idea of this path dependent approach, where you just start locally and you kind of think your way through and you say, next step, I can take the best next step, and then the best next step there. And then that will lead me to salient technical issues. So when you're in one of these, unknowable or unknown domains, you can use this kind of path dependent method or path dependence method to get you to these salient technical issues. But of course, as we just talked about, sometimes that can even introduce more complexity. And so you're never really safe. You really need to kind of think through how you're going to get yourself around or through the complexity. Sometimes you just need to embrace it. And I'm sorry to say I have no clear answers to that. I'm just presenting these ideas to you. Sometimes the diverse effects on a system are features to work with rather than around. Of course, in the last case, we saw that if you add a new feature in a bunch of different ways because your software supports a bunch of different versions or operating systems or whatever, that can be a huge amount of complexity. But sometimes, when you think about a system where if you have a single input, it has multiple responses or multiple consequences. Sometimes you need to work with that complexity instead of kind of around it. And then sometimes nonlinear processes themselves are often a feature of actionable outcomes. So sometimes we'll complete an issue and we'll have some unintended consequence, or we'll have some multiplicative thing that results. Again, if we go to back to that issue, we might or back to that feature, we might create a feature and do very well at it. But when we're trying to implement it in different versions and different, supporting different operating systems, so on and so forth, we create this multitude of things that we need to then do quality control on and check for bugs. So there's this article from Stack Overflow blog called The Tech Toolbox Between Chaos and Rigidity. So this is where they talk about how a lot of teams will approach technical stacks or the different technologies that they use. And so they give these kind of two examples, these two extremes, and then discuss that there's some middle ground that you can find that satisfies the needs of your team. So some teams will approach tech stacks and toolboxes from what they call the Wild West approach, which means that there's full autonomy and absolute change. And so sometimes if you have highly innovative teams, sometimes if you're doing a lot of improvisation, sometimes if you don't know what tools will work on a certain problem domain, you have to use this. You have to try different tools, see what works. And you have to give your team autonomy to do this. You can't lock them in to a workflow. So that's great if you want to do a certain type of thing, if you're namely working in one of those unknown or unknowable areas and you just need to try things to see if they work. But the problem is, of course, is that when you do that, you risk the sprawl of issues and technologies. And, sprawl meaning that you try all these different technologies, you spend all your time on these different technologies, you have to learn all of them. And so it becomes very time consuming as well as resource consuming. Furthermore, sometimes it's hard to reuse tools and past solutions. So getting from where you're trying all these tools to see what'll work to a workflow where you have reproducibility, where you can reuse tools and past solutions, is sometimes kind of a hard transition. It's not just that you pick the best things and promote them, it's that sometimes it's very hard to actually get a workflow together from that type of approach. The second approach is lock it down approach. So some teams will do this, especially the top-down managed teams, where there is no autonomy in terms of using different types of tools. Like a lot of teams will have a specific tool that they have for a task, like you have to use Zoom or you have to use Microsoft Word or something like that. And they, provide you a lot of sort of constraints. You have to use a single solution from the start, and there's no sort of experimentation allowed. It's great that you can do that, and a lot of times it helps teams, and it's in this known area, so it's good. It should be able to manage your time wisely and your resources wisely. So it's easy to reuse past solutions and past tools. But the problem is that the world changes. And so as the world changes, you may have to make these hacky and costly kludges to sometimes if you're working on a problem that you don't exactly know how it works, you have to make sort of adaptations to your tool, to your technical stack. Sometimes you have to migrate away from things. And so it's harder to, it adds complexity to your project. So you can take both of these extreme views and they both have their problems. And then if you say, okay, well, if we find the happy medium between them, we take a wild west approach some of the time, and the lockdown approach the other part of the time will be okay. That may be true, but you can also run into problems by kind of mixing them as well. So it's, this is just to say that like there are different strategies you can take to managing your toolbox to reaching that known region, but even then you have problems. So we can also map complexity to an agile framework. So we talked about, or we'll be talking about Kanban boards next time. I'll be going through a Kanban board. And remember, Kanban boards are where you have like a to-do column of issues. You have these different categories of priority, and then you have a finished category. And it's like a ticketing system where you close it out and you remove it from the board when you're done. But the problem is that's all linear. So it doesn't deal with complexity well, it doesn't deal with nonlinearity well. So people have recognized this and they've created tools that kind of use that Kanban approach, but in a networked and nonlinear way. So the first tool is this tool, Network Kanban. This is by Jürgen Appelo. This is from kanbantool.com. This is a case study where they work with this network Kanban board where the issues aren't in this linear arrangement, but they're in this network arrangement where you can go from one issue to another. You can go to one to several issues, depending on your version, your priority, and then that leads you to other options. And there's this network structure. There's also this nonlinear flow where you have you can go from issue to issue, but you can backtrack different issues. You can introduce feedback loops and other nonlinear effects in the Kanban flow. So this is another example. Um, and so the idea is what complexity wrought, basically non-sequential project stages, ill-defined issues in project states, and technical expertise that is non-contiguous over time. All of things of which we've talked about. And these Kanban approaches kind of solve some of these problems, but not all of them. So we need to have resulting project management techniques that sort of manage complexity. We start with the Kanban board, which is fairly linear. We recognize that we have these sources of nonlinearity or complexity. And so we need to kind of come up with project management techniques that'll resolve those to some extent. So we can have things like multiple entry and exit points for each issue. We can also have different types of representation within the same project. So we might have a linear workflow, a a web-like workflow and a circular workflow, all for different instances of the problem, all for different types of thing that we're trying to do. And then decentralized access to the entire project, where we don't let everyone get access to the project. This is like, of course, when we're doing like open source, where we don't want to give everyone the ability to issue a pull request. Maybe only certain people can issue pull requests, and then the rest of the people want to contribute through some other intermediary way that can be then, checked for errors and then incorporated. So we don't have to manage an overwhelming amount of complexity. We kind of decentralize access and plan for that. So this is an example of network Kanban. So this is our Kanban board where we have a backlog to do, and then it goes right where it's done. That's the conventional linear Kanban board. And then this networked process is where we have this linear sort of core, but we have these feedback mechanisms and these mechanisms that jump over other issues. So we have these paths that are, nonlinear basically. And so this is, depending on maybe certain conditions that are met in the project, or, we might have different workflows that vary in different ways. We can utilize these pathways and it can make things easier to manage for different instances. The one on the right, of course, is another example of a nonlinear workflow where we start with a linear path and then we branch off. We also have these feedback loops, and you're beginning to see that, you can move in different, you have many different paths that are possible through the different issues that are open. And the question is, we can solve them in different ways given different conditions within the project. So this is this article, The Optimal Way to Use Kanban Boards to Streamline Your IT Operations. this kind of gets into how IT operations teams will use Kanban boards, but then, you can use Kanban boards in this networked way, depending, if you're doing other types of projects. And so to finish up, I want to talk about how we can have these open-ended approaches to open source. So let's consider a system with both a prerequisite and an outcome. An objective that optimizes this process is not relevant. So we might have these open-ended processes where we have some prerequisite, we have an issue, and then we don't assume any outcome. We just kind of assume, like, it's kind of like the uh, adjacent possible technique, where you have like these local decisions that you make, these local sets of options, and they lead you to a new path. So you don't have this necessarily this fixed outcome. We have some objective that we want to meet, and we have a prerequisite, but we just do this locally. We keep making decisions, and we end up in different places depending on the decisions we make. So this is an example of the sort of the technological history of the videotape recorder. And you can see that you have all these different innovations that occurred from like 1890 down to 1956 when the first videotape recorder was created. And you can see that the development of this technology wasn't linear. They didn't set out to make a videotape recorder from 1890. They may have set out to do it like from about 1950 on, but they took a lot of technologies into sort of the pipeline, and those technologies had sort of their own developmental trajectory. So you take the technologies that exist, you put them together, you kind of work them out, and what you have is what's available to you, and then you work them out into this videotape recorder. So could we have had a better, more streamlined development of the videotape recorder? Probably. We didn't, because we have all these contingencies that come from the source technologies and things like that. Finally, we look at patents, and the patent space is actually a great example of an open-ended system. This is a study that talks about open-ended technological innovation. So thinking about different technologies that or forms of technology that emerge over time, we see that there are a lot of unanticipated innovations. So when we're thinking about project management, we kind of always think about, well, we can plan out these innovations and they'll all work out, and we'll end up in a place in 10 years that is, innovative and unique. But a lot of times you'll end up creating new things that you didn't anticipate, or running into problems you didn't anticipate. And sometimes they're outside of your mental model of categorizing things. So in US patent data, if you look over almost 200 years of data, you notice that new forms of technology emerge over time, like the video recorder or the video VCR. And, sometimes those rely on unanticipated innovations that drive forward this new thing. And then both of these tend to transcend previous categorical systems. So when you have a category like, in 1890 of recording devices, VCR it wouldn't really fit into that scheme. It's something new. It's something we don't know how to deal with. So, with patents and with inventions, you see this sort of open-endedness. You see this sort of managing complexity and getting to a new place. And then how do you manage your projects around that? Well, it's not at all clear. So when you're thinking of your roadmaps, you have to consider that you might be creating new things. You might end up in a new world or a new space in 10 years.